Here's the question on the table. Did the universe come from nothing? And I'm going to tell you something that's going to bother you, maybe for the rest of the night, maybe for the rest of your life, if you're the type who lets things bother you properly. The honest answer is that physics has never once, not for 1 second, dealt with nothing in the way you mean it. Every single time a physicist says the word nothing, what we actually mean is something, a vacuum, a field, a state with the lowest possible energy, a geometry of space-time curled up so tight you can't see it. We have never gotten our hands on true nothing. Not once. And the fact that we can't get there, that even our best equations refuse to let us get there, is one of the strangest and most important facts about the universe you live in. So tonight, I'm not going to give you a creation myth with Greek letters instead of gods. I'm going to do what I always do. I'm going to start from the bottom, brick by brick, and we are going to build this thing up together until you see exactly where the mystery actually lives. Not where people think it lives, where it actually lives. Because most of the popular talk about the universe coming from nothing is sloppy, and I spent my whole career hunting down sloppy thinking and shooting it on sight. I'm not going to stop tonight. Let's start with the easiest case, the one even a freshman could follow, and then we'll climb. You know what a vacuum is. Empty space, no air, nothing in it. That's the layman's vacuum, and it's a perfectly good word for everyday purposes. But quantum mechanics doesn't let you have that. Quantum mechanics has this rule, the uncertainty principle, that I assume most of you have heard of and maybe half of you actually believe. Heisenberg's rule says you cannot simultaneously know a particle's position and momentum to arbitrary precision. Fine, everybody knows that part. But there's a twin version of it that people don't talk about enough, and it's the one that matters here. You cannot know the energy of a system and the exact moment in time you measured it, both with perfect precision. Either energy and time play the same game, position, and momentum do. Squeeze down on the time interval, and the energy becomes uncertain wildly, genuinely uncertain. Not just uncertain because your measuring instrument is bad. Now here's where it gets strange. Take your empty box, vacuum, nothing in it, you'd swear. Pump all the air out, cool it down near absolute zero, shield it from every photon you can find. By the old classical thinking, that box has zero energy and nothing's happening inside it, but quantum mechanics says not so fast. For incredibly short intervals of time, the vacuum is required actually, to borrow energy from nowhere, conjure a particle and its antiparticle out of the field, let them exist for a flicker, and then annihilate each other and pay the energy back before anybody can catch them at it. We call these virtual particles. They are not metaphorical. They are not a cute way of talking about equations. They produce real measurable effects on the world you live in. I'll give you the cleanest example I know, and it's one I find almost embarrassingly beautiful. Take two metal plates, perfectly ordinary, electrically neutral, uncharged, conducting plates, and put them very close together in a vacuum, a few microns apart. Classically, nothing should happen. There's no charge, no field, nothing pulling them together. But Hendrik Casimir worked out, back in 1948, that those plates restrict which virtual photon wavelengths can exist in the gap between them, the way two walls in a room restrict which sound wave resonances can fit between them. Outside the plates, every possible vacuum fluctuation gets to exist. Inside the gap, only the wavelengths that fit between the plates are allowed. That mismatch creates a tiny but real pressure difference, and the plates get pushed together by nothing. By the vacuum itself, by the structure of empty space leaning on them. People have gone looking for that force in the laboratory and found it sitting right where the mathematics said it would be. Let that sit with you for a second. We are talking about a measurable mechanical force generated by two flat pieces of metal, caused entirely by what is and is not allowed to happen in empty space. If that doesn't convince you that the vacuum has structure, I don't know what will. So strike one against nothing. The vacuum of quantum field theory is not nothing. It is a roiling, structured, dynamic state, the lowest energy state of a field, yes, but a state nonetheless, with its own rules, its own restless activity, its own measurable consequences. It has properties. Things that have properties are not nothing. They are something dressed up in a word that fools people into thinking otherwise. Now, you're probably thinking, fine, Feynman, the quantum vacuum isn't nothing, but that's just a technicality, a word game. The real question is how you get something, particles, energy, matter, a whole universe, out of even that almost nothing. And that's a fair pushback. Let's go after it head on. Here's an idea that goes back further than you'd think, and it's one of those ideas that sounds like a joke the first time you hear it, and then turns out to be dead serious. In 1973, a physicist named Edward Tryon published a short paper. I want you to picture this. A short paper, not a book, not a grand unified theory, just a few pages proposing that the entire universe could be, in his words, simply one of those things that happens from time to time. A vacuum fluctuation. Like the virtual particles in my box, except this fluctuation didn't annihilate itself back into nothing in a flicker of a second. It kept going. It inflated, it grew, and 400 million years later, somebody invents the bongo drum, and here we all are. You want to know why this isn't just crackpot speculation? Because of a piece of bookkeeping that should bother you the first time you hear it, and then become one of the most satisfying things you'll ever learn in physics. Energy. Total energy. Add it all up, every particle in the universe, every photon, every bit of matter, convert it all to its energy equivalent the way Einstein taught us, and you get some enormous positive number. Fine. Now add up the gravitational potential energy of all that matter. All of it, pulling on all of it. And here's the trick. Gravitational potential energy is negative. It's a debt, not a credit. The further apart two masses are, the closer that debt sits to zero. The closer together, the deeper the well of negative energy. Now here's the punchline, and it's a real result, not a guess. When cosmologists actually run the numbers for a universe shaped roughly like ours, flat or very nearly flat, which is what observation tells us our universe actually is the positive energy tied up in all that matter, and radiation comes shockingly close to canceling the negative energy tied up in gravity. Close enough that within the bounds of what we can measure, the total energy of the universe could be exactly zero. Not approximately zero in some hand-wavy sense, possibly, genuinely, exactly zero, the way the energy of my virtual electron-positron pair in the vacuum is exactly zero before and after it pops in and out of existence. And if the total energy of the universe really is zero, then conservation of energy, that sacred law you all learned in high school and which I have never once seen violated in 50 years of doing this for a living. Conservation of energy does not forbid the universe from existing. It doesn't require you to borrow anything from outside because there's nothing to pay back. A zero state is zero. The books balance. You don't need a reservoir of stuff sitting around before the universe to explain where the stuff inside it came from, because net, when you do the whole sum, matter, and gravity, positive and negative, there might not be any stuff there at all in the only sense conservation laws actually care about. I remember the first time I really sat with that idea, turning it over, looking for the hole in it the way I look for the hole in every idea somebody hands me, because that's the job and I couldn't find one. That's rare. Usually you poke at an idea for an afternoon and it falls apart. This one held. Now, you're going to ask me, because anybody worth their salt would ask me, all right, fine, the energy books balance, but something still had to fluctuate. A fluctuation in what? Out of what backdrop? You can't have a fluctuation happening in absolutely nothing, can you? No space, no time, no field to fluctuate. And here, ladies and gentlemen, is where we hit the real edge of what we understand. And I am not going to dress that up as more solid than it is. This is where you have to bring in Alan Guth's idea from 1980, which he himself half-jokingly called the ultimate free lunch. Guth was wrestling with some technical problems in the standard hot Big Bang picture, why the universe looks so flat, why it looks so uniform in every direction when regions on opposite sides of the sky never had time to talk to each other and equalize their temperatures. And his answer was inflation, an unstable, high-energy state of the vacuum itself, not regular vacuum, a different kind, a false vacuum, sitting at a higher energy than the true, settled vacuum we live in now. driving an unimaginably fast exponential expansion of space in the universe's first fraction of a second. Doublings of size happening every 10 to the minus 30 something seconds, something like that, over and over, dozens of times. Before the false vacuum finally decayed down to the true one and dumped all that stored energy into the particles that became you, me, the chair you're sitting in, and every star you've ever looked up at. Here's why I bring up inflation in a talk about nothing. Inflation takes a microscopic patch, and I mean genuinely microscopic, smaller than a proton, and blows it up into something the size of the observable universe in a flash. So if you want to ask, did the universe come from nothing? What inflation tells you is that you don't need the original seed to be very big at all. You don't need a universe's worth of stuff sitting there waiting to expand. You need an absolutely tiny region of false vacuum sitting at the wrong energy, ready to roll downhill, and the geometry of inflation does the rest, stretching that tiny patch out to 100 billion galaxies and more. The seed can be staggeringly small. It can be small enough that quantum fluctuations, the very same virtual particle nonsense I described to you in the box at the start of this talk, are exactly the right size of thing to provide it. So now watch the pieces lock together, because this is the moment I promised you, where it gets strange in a way that should genuinely unsettle you and not in a comfortable, abstract textbook way. A quantum fluctuation, the same fundamental phenomenon that makes my two metal plates feel a tiny attraction in an empty box, happens to occur in a region that happens to sit in a false vacuum state. That fluctuation does not annihilate itself back into nothing the way the ordinary ones do. Instead, it triggers inflation. Inflation takes that almost nothing and stretches it in a fraction of a second into a universe-sized something. The total energy stays at zero the whole time, the book's always balanced, gravity's debt and matter's credit moving in lockstep. And what you end up with, 90 some odd years after a man named Hubble noticed the galaxies were running away from each other, is you sitting in these chairs listening to a dead man's voice ask you whether any of this started from nothing. I want to stop here and tell you something honest, the kind of thing I'd tell you over coffee rather than from a stage, because I think you deserve the real version and not the triumphant version. Everything I just described to you, the vacuum fluctuation, the false vacuum, the trigger into inflation, every bit of that physics is happening within a framework that already assumes quantum fields exist, that space-time exists in some primitive sense for those fields to live in, that the laws of quantum mechanics and general relativity are already true and already operating. I have shown you, as carefully and as honestly as I know how, that you can get 100 billion galaxies out of a quantum fluctuation in a false vacuum without violating a single law of physics. I have not shown you, and nobody has shown you, and I don't believe anybody currently can show you, where those laws themselves come from, or why there should be a quantum field at all, instead of strictly nothing, no fields, no space-time, no rules, not even rules waiting in the wings to be obeyed. That gap, and I want you to actually feel the size of it, not just nod along that gap, is the real mystery. Everything before it is physics, real physics, equations that make predictions you can go test in a laboratory or with a telescope. Everything after it, the question of why there is a something capable of having quantum rules at all, sits outside what any equation I know how to write can touch. I am not going to pretend otherwise to make the ending of this talk feel tidier. That would be exactly the kind of selling you something I warned you about at the start. Now let me take you somewhere stranger still, because I haven't even told you the part that I personally find the most beautiful and the most disorienting, and it comes out of a question that's even more basic than where did the energy come from? It's the question of where time itself comes from. And to get there, I have to tell you a story about myself, because this whole business of thinking about the totality of the universe instead of one particle at a time is not a comfortable habit for a physicist to get into, and I learned that the hard way as a young man from my own thesis advisor. When I was a graduate student at Princeton, working under John Wheeler, and Wheeler was a strange and wonderful man, the kind of physicist who'd hand you an idea so far out you'd assume he was testing whether you'd laugh at him. He called me up late one night, genuinely excited, with an idea he wanted to run past me before he forgot it. He said, what if there's only one electron in the entire universe? What if every electron we ever detect and every positron is the same single electron, threading its way back and forth through time, looking like a positron whenever it's running backward and an electron whenever it's running forward, weaving through all of history like one continuous strand? I told him I remember this distinctly, that it couldn't be right, because if it were true, there'd have to be exactly as many positrons in the universe as electrons, since every backward stretch of the path has to come back forward eventually. And as far as we can tell, there are vastly more electrons around than positrons. Wheeler, without missing a beat, said something like, maybe they're hiding inside the protons. We both knew that wasn't going to hold up. But here's the thing: that ridiculous, beautiful, wrong idea is the seed that grew into the way I came to think about particles moving through space-time diagrams, antiparticles as particles running backward in time, the whole machinery of what people now call Feynman diagrams. I didn't get the one electron universe. I got something almost as strange sitting right next to it, and I only found it because Wheeler had the nerve to ask a question about the entire universe at once instead of one particle in isolation. You have to be willing to ask the embarrassing, oversized question, because sometimes the wreckage of a bad, oversized question is exactly the rubble you need to build the right idea. I tell you that story because it's the same move you have to make to get anywhere on the question we're actually here for tonight. You cannot think about the birth of the universe the way you think about a billiard ball rolling across a table, with a clock ticking steadily in the background, counting off the seconds before the ball started moving and the seconds after. Time, in general relativity, is not a fixed backdrop. It is part of the geometry itself, part of what's being created, bent, and stretched along with space. So if you want to ask what happened before the universe began, you may be asking a question shaped like a square peg for a round hole, because before presupposes a clock that was already running, and if time itself is part of what came into being, there may have been no clock running to be before anything at all. This is not a dodge. I want to be very clear about that, because it's the kind of statement that sounds like a dodge and isn't one. Physicists actually tried to take this seriously and write down equations for it. There's an equation named after Wheeler and a collaborator of his named Wheeler-DeWitt that attempts to describe the universe quantum mechanically as a whole, not a particle in a box, the whole box, the whole universe, treated as a quantum system with a wave function. And one of the strange features of that equation, when you write it down properly, is that it has no time variable in it at all, none. The wave function of the universe in that formulation simply is it doesn't evolve, because there's no external clock for it to evolve against. Time, in that picture, isn't fundamental. It's something that has to emerge from correlations within the wave function itself, the way you can recover a sense of before and after from the entanglement between different parts of a quantum system, even if there's no master clock running the show from outside. And here's the part that, I'll admit, took my own tools and turned them back on me in a way I find almost funny. Years after my own work on quantum electrodynamics, a couple of physicists, James Hartle and Stephen Hawking, took the method I'd developed for QED, the path integral, the idea that to find the probability of a particle going from one point to another, you don't pick one trajectory, you sum over every conceivable trajectory it could take, weighted by how much each one contributes. And they applied that same machinery to the geometry of space-time itself. Instead of summing over every path a particle could take between 2 points, they summed over every possible shape space-time itself could take, weighting each possible universe history by its contribution the way I'd weighted each path an electron could take through a double slit. And they made a proposal. They called it the no-boundary proposal, that the very beginning of time shouldn't be thought of as a sharp edge, a wall you slam into and ask what's on the other side. Instead, if you go far enough back and treat time In a particular mathematical sense, the way you'd treat another direction of space, the geometry just smooths out and closes off the way the surface of the Earth closes off as you travel south. You don't hit a wall at the South Pole. You don't fall off an edge. You just run out of further south to go. There's no boundary, no edge, no before, not because something forbids it, but because the question stops making grammatical sense once you actually understand the geometry you're standing in. I am not going to tell you that proposal is proven. It isn't. It makes certain predictions about the early universe that people are still chasing down, still arguing about, and I'd be lying to you if I said the matter was settled. But I want you to sit with the shape of the idea for a second, because I think it's one of the most genuinely strange and beautiful things the human mind has produced. It says that asking what came before the beginning of time may be exactly like standing at the South Pole and demanding to know what's further south. The question feels meaningful because you're used to a world where every point has a further south. It stops being meaningful the moment you actually understand the shape of the thing you're asking about. So let me bring this all the way back around, because I promised you I'd build this brick by brick, and I intend to finish the building properly. Did the universe come from nothing? Here is the honest answer, the one I'd give you if you cornered me after this talk and wouldn't let me go until I gave you a straight reply. The nothing of everyday language, an absence, a void, a true and total lack of anything whatsoever was never on the table to begin with, not in any version of physics I know how to write down. What we actually have is a quantum vacuum that is restless, structured, and capable of measurable effects, sitting within a field theory that already presupposes the existence of fields and the laws that govern them. We have an energy bookkeeping trick that shows the total energy of a universe shaped like ours could plausibly be zero, meaning conservation of energy raises no objection to its existence. We have an inflationary mechanism that shows how an almost unimaginably small fluctuation could blow up into everything you see in the night sky. And we have, at the very edge of what current physics can say, anything coherent about proposals, serious, mathematically worked out proposals, not mysticism suggesting that the question of before the beginning might not even be a well-formed question, the way what's south of the South Pole isn't a well-formed question. Once you actually understand the geometry involved, what we do not have, and what I do not believe anyone currently has, is an explanation for why there are quantum fields and space-time and laws of physics capable of doing any of this at all, instead of a state with no fields, no geometry, no laws, no nothing, in the most absolute sense the English language can gesture toward without quite reaching. That gap is real. I am not going to pretend it's smaller than it is, just to give you a satisfying ending tonight. It is the single most honest, unsolved problem I know of in all of physics, and it has kept better minds than mine up at night for exactly that reason. Not because it's depressing, but because it's the one place where the usual trick, find the equation, sum over the histories, run the numbers, simply doesn't get a foothold yet. We don't even know if it's the kind of question physics is built to answer, or whether it's a different kind of question altogether, wearing a physicist's costume. So here's what I'll leave you with, and I want you to actually carry this out of the room instead of letting it evaporate over a drink afterward. Every version of nothing we have ever managed to examine carefully turned out, on inspection, to be something restless, structured, obeying rules, capable of giving birth to everything you can see and touch. Maybe that's because true nothing, the philosopher's nothing, is simply not a state the universe is able to occupy, the same way you can't write down a wave function for a particle with exactly zero uncertainty in both its position and its momentum at once, not because we lack the cleverness, but because the rules themselves forbid the configuration from ever existing. Maybe asking why there is something rather than nothing is like asking why a circle doesn't have corners. The answer isn't an explanation you discover. It's a feature of what the words even mean. Or maybe I'm wrong about that too, and there's a deeper layer underneath all of it that I will never live to see uncovered, a layer where the question finally gets the kind of answer that satisfies the way conservation of energy satisfies, the the way the Casimir effect satisfies when you finally see two plates move under a force generated by nothing more than the shape of the vacuum between them. I don't know which of those it is. Nobody currently alive knows which of those it is. And I want you to leave here tonight not comforted, but unsettled in the productive way, the way I've been unsettled by this question for the better part of my career. Because that unsettled feeling, that itch that won't quite resolve, is the most honest emotional response available to anyone who actually understands how much we figured out and how much we very plainly have not. Go home, and somewhere around midnight, when the rest of the world has gone quiet, ask yourself not why there's something instead of nothing, but why nothing was apparently never an option to begin with. Sit with that one. It's a better question than the one you walked in here with, and I promise you it doesn't have an easy answer either.